Okay, lab 6, hopefully we'll get to do this face to face, but I'm just narrating this lab as a reference. Okay, so lab 6 deals with ways of quantifying biological molecules using a special instrument called spectrophotometer. Okay, the process is considered spectrophotometry. Okay, typically that's a method used to quantify biomolecules. It's a light-based quantification method. So light means UV light or visible light. Okay, so spectrophotometry is based on how molecules absorb light when a light strikes through them. Okay, so typically light when they go through molecules that are dissolved in liquid, light may pass through them. We say that it's transmitted through them, or light may be reflected, scattered, or light energy may be absorbed by the molecule. Right, so if the object is liquid, completely dissolved in liquid, light is either absorbed or transmitted through, okay, instead of reflected. So it's either absorbed or transmitted. That's the two possibilities. So then spectrophotometer, uses a light, beam of light, either UV light or visible light, and it's gonna shine the light on the biomolecule that's fully dissolved in liquid, maybe water. Okay, so it's going to measure the transmittance of the light that's coming through the other side. Okay, so then transmittance is, that'll be the light transmitted through the sample that has your biological molecules, and that's divided by the light transmitted through the blank, which does not have the sample, it's just a solvent only. Okay, so that's the difference, will be the amount of light transmitted by your biological molecules. So percent transmittance will be transmittance divided by 100%, of course. So transmittance value will be received as either 0 to 1, 1 being 100%, so nothing is absorbed, right? And there's a kind of a negative log relationship between absorbance and the transmittance. Okay, amount of light absorbed by your molecule kind of inversely related to the amount of light that's transmitted. Okay, so it's negative log relationship. So if you have 100% light transmitted through your molecule, that means no light is absorbed by your molecule. That makes sense, right? So you use that principle in your quantification of your biological molecules. So the concentration of analyte, your biological molecule, you could just see in the solution, and its transmittance. Okay, there's some relationship. Okay, it's a kind of negative log relationship, because the more molecule is there, so there will be a more possibility that they will absorb light, then the light that's transmitted through will be much less. So there's a negative log relationship. Okay, but the absorbance and the concentration of analyte have a linear relationship. That's the key. Okay, so the more molecules are there, they will have a higher tendency that they can absorb more light. So there's a linear relationship between the absorbance and the amount or concentration of analyte you can see in your sample. Okay, so when you do this measurement in the spectrophotometer, you have to hold your molecules, the solubilized molecule, in a special container called cuvette. Okay, you need at least 2 cuvettes, one for your blank, the solvent only, the other one for your sample. So quantification of macromolecules like protein, DNA, RNA, using spectrophotometer. So the linear absorbance range of DNA, if you use UV light at 260 nanometer range, that can be absorbed between the absorbance and the concentration of the DNA. If your DNA concentration is just between 5 and 100 microgram per milliliter. Okay, it's above that, then the relationship will be changed. So it's only possible to do the reading between that range. And the linear absorbance range of protein, if you're using the protein as your sample, you may have to use 280 nanometer light, UV light, because that light is absorbed by protein molecules better, especially protein molecules with aromatic amino acid, ring structure amino acid, like tryptophan, tyrosine, phenylalanine kind of thing, and they will receive the light, and the more protein is there. So there's a linear relationship between 0.1 to 5 milligram per mil. So it's a very narrow range compared to DNA, right? So that's why you're not going to use UV light in quantifying protein sample. Okay. So major reference points for your quantification, especially DNA and RNA. If your DNA exists as in double-stranded conformation, okay, then observance density, so OD is optical density, it's a unit for your observance reading. Okay, OD1, okay, reading at 206 nanometer UV light is normally saying that you have this much of DNA, 50 microgram of DNA dissolved in 1 milliliter total volume. If you have that much DNA, normally observance that DNA can get is about 1 OD. Okay, but if we have single-strand DNA instead of double-stranded, okay, that observance value changes. So because single-strand DNA can absorb more light than double-strand DNA, because absorption happens on the base parts a lot. So so one observance value OD normally is achieved by less amount of DNA, like 33 microgram per mil. It's different. And then if you have RNA instead of DNA, RNA molecules are all single-stranded, right? So they have different structure, and they have U's instead of T's. And then it turns out one observance OD, 260 nanometer, is about 40 microgram per mil. So RNA molecules absorb a little less light than DNA that's single-stranded. Okay. If your DNA sample is diluted, okay, 1 to 100 dilution, okay, and when you do the absorption test at 260 OD, and the observance value came out to be 0.25 OD, then how much of DNA sample do you have? Okay, so what it's asking is, okay, you got 0.25 instead of 1. Okay, so you have a DNA sample, it's double-stranded. Then how much DNA would you have? Okay, you can go back here. If you have 1 OD, you have that much, 50 microgram per mil, right? What if we have 0.25 instead of 1? So that's about 1/4. Okay, so 1/4 of that is what? So if we divide 50 by 1/4, that's going to be what? What? 12.5 or something like that microgram per mil. So that's that. And in this case, you have RNA sample instead of DNA, and it's diluted. One thing that you didn't complete is it's diluted, 1 to 100 diluted. So whatever the concentration you get, okay, you have to multiply 100 to get the concentration of undiluted DNA sample. You have to always consider that dilution factor. And then in this case, RNA sample you got 0.1 OD at 260. So RNA right here, if you have 1 OD, it's 40 microgram per mil, but instead you have 0.1 OD, it's about 1/10. So probably 4 microgram per mil is the concentration you have, right? But it's diluted 1 to 10. Okay, so it's 10 times more. So it's going back to that 40 microgram per mil. That's how much RNA you have. So that's how you do the quantification. And then the ratio between the 260 observance reading and then 280 observance reading, okay, the ratio, so the observance reading at 260 divided by the observance reading done at 280, if you divide the observances, the ratio gives an idea that if your DNA or RNA or protein samples are pure or not. Okay, especially here, if the ratio 260 over 280 is close to 2, then most likely your sample is mostly made out of RNA molecules. Okay, because RNA molecules, single-stranded, they may absorb more light on 260 compared to DNA. Okay, and they absorb less light on 280 UV light. Okay. And then if it's a pure DNA double-stranded, okay, the ratio 260 over 280 is about close to 1.8 value. And then if you have all pure protein only, then ratio becomes much less. So it's a 0.6. Okay, so if you have an idea about how pure your DNA, RNA, or protein sample, you can do the two readings on the UV, 260 and 280, and do the ratio of the observance, then it'll give you an idea about how pure your sample is. Okay. So what if your ratio value was between 1.8 and 2? Then what that means is, it's not pure DNA or it's not pure RNA. It's a mixture of both, right? Okay, so example problem, your plasmid DNA preparation was diluted to 1 to 100, so 1 to 100 dilution was there. And then you analyze at 260 and 280. Okay, the following values observed from your analytes. So 260 reading 0.75. It's a DNA, double-strand DNA. So 1 OD was 50. So 0.75 is what? 0.75 times 50. Then you can guess the concentration. To that, you have to multiply 100 to get the, the original concentration, right? And then what about the OD? 260 over 280. 0.75 divided by 0.39. What do you get? If you do it quickly, 0.75 divided by 0.39, it's about 1.92, which is higher than 1.8. So it's not a pure DNA, close to 2OD, so it's probably a mixture of DNA and RNA, right? Okay, so the lab exercise, hands-on exercise. So you will be given with, I guess you will use the DNA that you isolated from E. coli cells, BIOL221Lab6-1. Okay, so you need to determine the concentration of DNA using the spectrophotometer reading, so 260 reading and 280 reading, and see how much DNA you have. So since you only have like 50 microliter only, you have to dilute it, maybe 1 to 100. So 10 microliter of your DNA sample mixed up with 990 microliter of water, and do the reading at 260 and 280. Okay, if you haven't done it in the previous lab, this is the time you can do it. And not only that, you can do the reading at 280 as well to get the ratio and see how pure your DNA sample is. Okay. And then the second part is the protein concentration assay. So DNA RNA is straightforward. You can use the UV light observance 260 and 280. But the protein sample, if you have protein, it's not easy because, protein samples observe very little bit of light. So we said something about here, protein, the linear range is very narrow, and you have to use 280 nanometers. So that's why you don't want to use UV light when you try to quantify your protein. Okay. So if you want to quantify your protein molecules, instead of using UV 280 or 260, you want to use a visible light, especially after staining your protein with something that can easily observe the visual light. Okay, so that's why there are 3 different color chromogenic reagents that you can add to your protein before your protein will be quantified, and then those chromogenic substances will better observe the visible light. And then, so since those chromogenic substances will bind with the protein almost like equal ratio, and so the quantification of the chromogenic substance concentration will be correlated with the observance of the visible light that they will do in the spec. Okay, so among those different chromogenic substance choices, okay, I think Bradford assay solution is the best, I guess, prevalently used because it has such a nice spectrum where it can observe the light, especially the in terms of the range it can cover. Okay, and that is better. So you'll be given the Bradford reagent solution, so you can add the solution to your sample protein. So you'll have maybe 2 BSA unknown. BSA is bovine serum albumin protein, special protein. Then you'll have prepared unknown BSA solution. You will be asked to quantify those unknown solutions using the Bradford solution agents. So in order for you to do that, you need to create a standard curve before you quantify it, because without the standard curve, you don't know what the relationship between the observance and the concentration is, right? So for that, you need to create a standard curve. Okay.